I have no idea.
But not next week.
We could just not have the test.
Good idea.
Good one.
It's a good idea.
That's a good idea.
Yeah, right. We should.
That is not a good idea.
Wait,
Why not?
we only have this
You're
one.
right, it's a great idea.
Okay, you know what? Then you guys just do independent study then.
Oh wait, it's this chapter and one more chapter and we're done.
Yeah.
Oh no, that's so fast. I'm not ready.
Wait, really?
The last chapter is also pretty intense, but not as intense as this.
Oh.
Okay, so we did number 1 yesterday. Number 2, I guess well, at least I'm gonna set them all up. Some of them you might need help on. So what?
Solve number 2.
Yeah, we can. Yeah, I tried to solve it. I couldn't.
Okay, well let's set up why did you write the integral?
I think so.
Okay, let's draw the graph. You should always start by drawing the graph. It says find the area of the region that lies within the circle r equal 1, which is this. And then the parabola. Now, we did this in PCH. Let's do a review, since you guys probably forgot everything.
Yeah, I couldn't figure out how to draw it either.
I just
Sorry.
thought it was.
Any equation in this form is going to be a conic section. This number here is the eccentricity of the conic section. So if the eccentricity is 1, you know it's a parabola, right? Everybody here took PCH and Algebra 2, come on. What if that number is like a fraction smaller than 1?
Then it's not.
Then it's an ellipse. And what happens if this number is
Oh,
greater than
hyperbola.
1? It's a hyperbola. You mean we really didn't learn eccentricity in PCH? No, we did. And you, Cho, are going to be in that event.
Okay.
Next me.
I'll collect that.
Okay, so the easiest way to graph these conic sections, and we did this in PCH before. No, you plot the quadrantal angles. So, plug in 0, go. Plug in 0. You get a half. Plug in pi over 2,
1.
1. Plug in pi,
0.
no, undefined. 1 over 0 is undefined. And then plug in 3 pi over 2, 1. So, here's Johnny.
Hey, I got that.
I can say it was an ellipse.
No, it's 1. The eccentricity is 1. It's a parabola.
Maybe it says it's parabola.
And yeah, it's.
In the question it says
Oh my
it's
goodness.
parabola.
Oh gosh, I can't believe we forgot that. So it says find the area that's inside the circle but outside the parabola. Actually, we did this in BC. Except we did it with 1/2 r squared d theta, but it's the same thing. So we're going to do a double integral. We're going to integrate with respect to r first and then theta. You know why? Because theta goes from negative pi over 2 to pi over 2. Those are the constants. Okay? You always have to do the ones that have the constants last, because you can't be plugging in variables on the last step.
Wait, why is it not from pi over 2 to 3 pi over 2? Oh, that's the wrong.
Because that would go like this.
It could be from 3 pi over 2 to.
Can you do 0 to
No, because that doesn't make sense.
Oh, that's
You
fine.
could go 3 pi over 2 to 5 pi over 2.
Okay.
It's got to be numerically in order, people. It's like on a number line. But polar goes like this, right? 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi, and so forth. You got to do it in order now. Okay, and then what about r? R goes from here to there, right? So what's the equation of this curve?
Oh, it's right minus left.
No, out minus in. But then we're not doing that. We're going. R goes from, see, R is the distance from the origin, right? You're going out like this. So from here to here. So what's that? What's the equation of this
1
curve?
minus.
No, 1 over 1 plus cosine theta.
Oh.
It's right there. And what's the equation of that outer curve there?
1.
1. So
Oh.
this is your integral.
Oh, I switched.
Now, as it turns out, this integral is very difficult to compute. What? So I heard.
Yeah.
Okay, so here we go. dr. What is the integral of 1 with respect to r? Oh, we forgot the r. Duh. It's r dr d theta, not
So for
just dr
everything,
theta.
it's just gonna be r dr theta.
Yeah, because that's like here. If you remember we drew this picture yesterday, if you take a tiny rectangle like that, r dr d theta is the area of the tiny infinitesimally small rectangle. Okay, And then, if you have a three-dimensional shape, then you just multiply it by the height,
Oh,
which is z. For 3, 4, and 5, whatever z is, that's what you multiply this by, because that represents the height of the thing. For three-dimensional pictures, but in problems 1 and 2, it's only two-dimensional. Anyway, what is the integral of r dr? 1/2 r squared. Hey, that's the stuff from DC calculus, right? Remember, 1/2 r squared d theta? That's where it came from. So, and then you gotta go from 1 over 1 plus cosine theta to 1. Shall I factor out the 1/2? Too bad, I'm gonna. 1/2, plug in the top thingy, 1, minus plug in the bottom thingy, 1 over 1 plus cosine theta quantity squared. Now you gotta integrate this with respect to the theta from negative pi over 2 to pi over 2. Okay, so this 1/2 can be thrown outside. Now, how do I integrate that? That's the problem, question.
can you do from 0 to pi over 2?
Yeah, you can go 0 to pi over 2 and times by 2 if you want. You wanna do that?
So 1/2.
Okay, let's do what Haas said. Go from 0 to pi over 2 and times it by 2 and okay. Plus it's easier to plug in 0 than negative pi over 2 anyway. Now, how do you integrate this? This is the problem. What should I do?
Trig substitution.
Oh, combine.
No, it's already trig.
Combine.
Make a least common denominator. So 1 plus cosine theta quantity squared in the bottom. What's gonna go on the top? 1 plus cosine. Okay, no, you guys are good in that. If you multiply out the top and subtract the 1, what's gonna be left on the top?
Cosine squared theta minus
2 cosine theta
Plus cosine.
plus cosine squared theta and then d theta. Okay, so that's our integral now. Now, did we learn something when we did our integral review? Like, whenever you have a rational function with sines and cosines, how can I change that to simply a rational function?
Oh, are you doing Z?
The z substitution.
No,
No.
no.
Yes.
Ooh.
See, so Cho actually came in for help on that yesterday.
I didn't
What about the rest of
start-
us?
I didn't start it actually.
Who finishes the homework yesterday?
You guys are supposed to be the top students in the school. You only have like 5 homework problems to do every night.
But I don't do it.
Okay, you.
No, I think.
You didn't even say anything after I wrote a letter. You too.
No, I was just gonna say that I think the top scholars is the kid in AP Physics C.
Well,
Well, you're here, aren't you? That means you got a 5 on the AP exam in BC.
Yeah.
Okay, let's just go on. Okay, do you guys even remember the z substitution? Z equals, okay, if you have to just remember one thing about the z substitution, z equal tangent x over 2.
Yeah.
Okay, let's put theta, since they have theta here.
can we use T for Z?
Yeah, you can use whatever, it doesn't matter.
Because the Z's and the T's get mixed up.
Not if you put the line through it. Oh my goodness. Okay, so what do we do here? How did we derive this way back when? In August. I just did it for Cho yesterday. What was the first step? Cho looked it up in a book.
Oh, you write
Wait, no. You
you
do
write the
the
thing out.
half angle.
Formula thing.
Wait, what?
I guess you could do that like 1 minus cosine theta over sine theta.
I would have had to remember that.
Yeah.
What did I do yesterday, Cho?
Yeah.
Wait, oh, sine.
I went like
over
this.
two.
Tangent theta over 2 is z over 1, right?
Yeah.
No, I don't think I did this yesterday. So that's the square root of z squared plus 1. I don't think I did that yesterday. What did I do yesterday? I tan inverse both sides. That's what I think I did. I think I went tan inverse z equals theta over 2. So theta is equal to 2 times tan inverse z. So what does the picture for tan inverse z look like? Tan inverse z looks like this, z1. It's the same picture. 1 plus z squared. That's the same picture. Yeah, but that... You know what? Oh, I got it now. So, tangent theta over 2 is equal to
Sine.
1 minus cosine theta over sine theta or sine theta all over 1 plus cosine theta, or plus or minus the square root of 1 minus cosine theta all over 1 plus cosine theta, right? Those are the three half-angle identities that you guys are writing down furiously because you can't remember them.
Yes.
Okay, which one am I going to use here?
The one with the one denominator at the bottom, right?
The first one.
The first
Yeah,
one.
the first one.
You're gonna have to see these one.
Okay, wait.
You can lift and separate.
No, wait, something's not right
Wait,
here.
didn't you take the derivative?
Oh yeah, that's what I did first. So dz is equal to secant squared. No.
No,
I did this and I took the derivative of it.
Yeah.
So 1 over, I just did see, look, that's what happens when you get old. I just did it yesterday and then it's just gone from my mind. 1 plus z squared dz is equal to 1/2 d theta. So therefore, d theta is equal to 2 dz all over 1 plus z squared. Okay, there.
Oh wait, you inverse, tan inverse both sides and then you took.
Yeah, I tan inverse both sides and then I took the derivative of it with respect to theta. Right there. Okay, now, we also need to come up with expressions for cosine theta and sine theta so we can substitute it in here. Okay, so, any ideas?
You do the same thing.
The formulas.
Okay, here, this is what I would do. If theta is equal to this, then wouldn't cosine theta be equal to cosine of 2 tan inverse z, correct? If you take the cosine of both sides. Okay, now, how do you compute the cosine of 2 times this? Well, you gotta use double angle identity, right? And this is tan inverse z right here, so which identity do I wanna use for cosine of 2 something?
Wait, can you not just use the picture?
Yeah, but then you gotta use the double angle identity. You cannot just go, tan inverse z and then times it by 2. You gotta use double angle identity.
2 cosine squared.
Okay, 2 cosine squared theta, which is tan inverse z minus 1, right? Cosine of 2, I don't want to use theta because we got another theta. Cosine of 2x equals 2 cosine squared x minus 1, right?
Wait,
Yeah.
I'm sorry, where'd you get that from? The cosine theta equals.
That's what we gotta find so we can substitute it into this.
No, what I was wondering.
We have to find an expression for cosine theta and sine theta so we can plug it in here.
Is it not just 1 over square root of 1 plus z squared?
No, because that's not theta, because that would be theta over 2. See the 2 here? This is, so, I just made the triangle just for this, just for that only. We did this in August, Park.
No wait, I don't know where you got that from.
I took this equation and I cosine both sides.
Okay.
That's what I did, that's all you got this. And the identity for cosine 2x is 2 cosine squared x minus 1. That's the identity.
Yeah. Wait, what is you? What's the purpose of doing that?
Because we need to find an expression for cosine theta so we can plug it in here.
Oh my god.
I didn't think I was going to be deriving these again. Ultimately, you got to memorize these. You know what? Oh, I thought we were going to finish early, but we're not. Okay, now how do I find the cosine of tan inverse z? That's what this triangle is for. So what is the cosine of tan inverse z right here? What's the cosine of this angle I just drew?
1 over.
This over that. So 1 over that, right? That's squared times 2 minus 1. So what you do is you simplify that. So that's 2 over 1 plus z squared minus 1, which is 1 plus z squared. See, this is a different than what I did yesterday. And so you get 1 minus z squared all over 1 plus z squared. There you go. That's what cosine theta is. That's cosine theta. And then now, how do I find sine theta?
Just add it.
You want to sine both sides, or you want to just draw a triangle for that?
Let's draw.
Okay, let's draw the triangle.
What is the opposite?
So cosine theta is adjacent over hypotenuse. So wouldn't this leg here be the square root of this squared minus that squared? And so you got the square root of 1 plus 2z squared plus z squared minus 1 plus 2z squared, oh that's z to the fourth, yeah, sorry. Minus z to the fourth. These cancel out, these cancel out. So you got the square root of 4z squared, which is just 2z, assuming z is positive. So looking at that picture, what is sine theta? Opposite over hypotenuse, 2z all over 1 plus z squared. There you go. Now, when you guys took the test back in August, I believe you guys just memorized those, yeah? But what I did just now is one way of deriving them. Okay, now we can actually start to do the integral. Woo! Okay, so here's the integral. I'm gonna erase everything else, because we need the board.
Wait. Sorry. Why did you find sine theta? Is it?
By drawing the triangle for
why?
cosine.
Why?
Because we need to, oh, there's no sine thetas in here.
Yeah.
Yeah, but then the one in the test might have sine theta on it. So that's what the z substitution does. If you have a rational functions with sines and cosines, you plug all of these things in, and then you'll get a rational function to solve. So let's do that. So 2 cosine theta. Okay, look at those substitutions. What is 2 cosine theta?
2 minus.
2, 1 minus z squared all over 1 plus z squared plus cosine squared.
Oh my.
1 minus z squared over 1 plus z squared squared over 1 plus cosine theta, which is 1 minus z squared over 1 plus z squared squared times d theta, which is, what is d, where's d theta? 2 dz all over 1 plus z squared. There you go. Hey, looks like it's going to be pretty decent. And what are my new limits of integration going to be? The original one went from 0 to pi over 2. What are my new limits?
Negative 1 to 1.
No.
Why not?
Okay, remember,
It's
this
the-
was your substitution. That was your original substitution. Z equals tangent theta over 2.
Oh, I lied.
So what if theta is 0? What if I plug in 0 for
Oh,
theta?
0
What is
and
z?
1.
0 and
0. And what happens when I plug in pi over 2 for theta?
Fine.
No. Pi
Oh,
over
yeah.
2 over 2 is pi over 4. Tangent of pi over 4 is 1. Okay, you know what? That's as far as I'm taking you. You guys gotta finish that. That's just algebra.
I couldn't
It's so
get
big.
the answer.
What?
How would you-
Okay, I'll go one more step. Can I erase this?
I don't even know where you would start on that.
Oh,
Simplify!
my favorite.
Yes, oh gosh. I'm getting hard. I'm getting weak.
Don't
No, I'm sorry. You guys gotta do algebra.
I didn't get the answer though.
Yeah, so, but I want them to try because they didn't even try.
Okay.
Cho, don't worry, we're gonna do it, but you guys gotta do something. It's like, I'm doing all the work. Okay, see? Finally, somebody feels guilty. The others of you is like, just tell us already. Okay, I'm gonna tell you right now, one of these is on the test. It's gonna do, it'll be
The
one.
exact problem?
Can you plug that into Wolfram?
Oh, do you use substitution or something?
No,
No,
simplify it,
just
simplify it.
Just make
Do
them
algebra
simple.
1, it's called algebra 1. Okay, now if you wanna punch it into Wolfram Alpha and get an answer, go ahead, Cho, but that's not gonna help you on the test.
Wait, why wouldn't you like use substitute for 1 minus z squared over 1
But
plus
just
z?
simplify. Like, do the bottom.
And then what would be du then? Exactly, that's why simplify it first.
I don't remember how to do it.
Wait, simplify as in like multiplying it out.
Okay,
and
so
adding everything
if
in.
I were me, this thing right here, I would multiply top and bottom by 1 plus z squared, quantity squared. That's what I would do, to simplify it.
Oh.
Multiply top and bottom by 1 plus z squared, quantity squared, and then you won't have any fractions anymore. You won't have fractions within fractions.
Oh.
Okay, too bad, we're moving on. Find the volume. You know what, in fact, all of these, did you guys even set up the integral? Okay, I'm just gonna set it up for you, and then you guys gonna have to do it. You guys,
I tried to.
I did.
what would happen if you have to do this independent study,
Can you do
where you have to do all the learning on your own?
I'll break this.
I wouldn't
Then you wouldn't do it.
It wasn't
Yeah.
necessary.
And then you do it. Okay, fine, now, okay, 3, 4, and 5 are, Okay, we're gonna do a double integral, are all three-dimensional figures now. So you're gonna have R, Quinn, I'm still waiting on 2 worksheets.
You're still what?
Waiting on 2 sets of worksheets.
From phone.
Did you even pick up yours yesterday?
She came home yesterday, she went home early yesterday. She was sick.
Oh, then you stopped by here to pick it up, yeah? Or you downloaded it from the website?
No.
Luckily, I kept them. Pick it up from that.
How do you go home early? You leave.
Go to the attendance office, or you gotta go to the infirmary first, and then they'll send you. Why, you planning on something?
No, just wondering.
Okay, so this represents, okay, look, again, I'm gonna draw it. So whatever omega is, if you do it in polar coordinates, see, this thing here represents that kind of rectangle of infinitesimal width. But now we have a three-dimensional thing we gotta compute a volume of. So there's a surface up here, right? So then you gotta multiply that by the height, which is the z coordinate. So whatever they give you for z, in this case, sine of the square root of x squared plus y squared, right? That's what z is. And below by the unit disk. Oh, why didn't I just draw the unit disk? So unit disk is easy, right? So r goes from
1.
0 to
Oh, sorry, XY.
1, no 1,
Oh.
because it's always 1, right?
Yeah.
And theta goes from 0
Zero.
to 2 pi. So it's actually really easy in this problem. You know why? Because both are constant. So, you know, because usually one of them is going to have variables in it, like the first problem we had. But they're both constants now, so it's easy to compute. Now, when you compute an integral in polar coordinates, what is x squared plus y squared?
R.
R squared.
Squared.
So basically, this thing here is just sine r. So how do I wait? I'm going to call on somebody here. How do I integrate r times sine r? What technique would I use? No. Park, what technique would I employ? R sine theta. You guys are supposed to be integral experts.
Oh.
Wait, R sine R.
What is
R
that?
sine R.
Oh, integration by parts. No.
Yeah. So more specifically,
Oh no,
it rhymes with mabular.
Oh, tabular.
Okay, so tabular. You got
How do you know whether you use integration by parts versus tabular?
tabular. Oh, yeah, tabular. One of the parts has to be differentiated down to 0. So like basically a polynomial. Yeah. Okay, I'll leave the rest to you because that's a really easy integral. Okay, let's do a quick review. R, really?
Oh,
Yeah,
it's a
really?
system.
Okay, so in this column here, you take derivatives, so 1 and 0, right? This column, you do antiderivative. So that would be negative cosine R, negative sine R, and then you go booga booga plus minus. Is that familiar?
Oh yeah.
So the antiderivative of r sine r is going to be negative r cosine r plus sine r. And then you got to go from 0 to 1. Okay. Well, you're going to have a cosine 1 and a sine 1 in the answer. Is that what it says on the bottom? Since I'm not going to walk
Yes.
in. Okay, so. Okay, let's move on. Number 4. Find the volume of the solid bounded above the plane. So here, just set it up already. R d theta. And then what is z? Z is y plus b. Below by the xy plane and on the sides by the cylinder. So that means looking at the top, since it's the cylinder, this is basically the circle x squared plus y squared equal b squared then, right? Because except in 3 dimensions, it's a cylinder, yeah, like this. Okay, I think we can do it. So if we do this in polar coordinates, what are the limits of integration for r? R is going to go from here, so it's going to go from 0 to b, right? Because the radius of the circle is b.
Oh.
You got to think polar coordinates. You can't think rectangular. You're going from the origin outward, like that. You're thinking like this. Okay, here like this. You're going from here to here, 0 to b. And then what about theta? Link 0 to 2 pi. Okay, so how do you do this integral? Well, we got to convert this into polar. What is y equal to? Polar coordinates?
Square root of.
No.
What?
y equals
Oh,
R.
r sine theta. Okay, I will leave it to you, that's an easy
Oh
one.
wait, what do you do with the z equals y plus b though?
He's a constant.
Z.
B is just a constant.
Oh.
So you're gonna get r sine theta plus b. Yeah, so you're gonna have a b in your answer. Okay, that integral, come on, that's nonsense. Number 5, find the volume of the solid bounded below by the xy plane, above by the sphere, and on the sides by the cylinder. So that's x squared plus y squared equal 1, right? Come on, that's easy. Okay, so double integral again, r dr d theta. Okay, but on the top is a sphere. We have to write the equation of this sphere in terms of z, because you're going to put z here, yeah? Z is the height. So you have to solve for z in that equation. So I'm going to erase this. Okay, you want me to be nice on the next test? On that problem, you want me to go hint? You
Yeah.
got to use z substitution, and I'll give you the 3 formulas.
Yes.
Yes. Please.
I'll think about it.
I
I'll
probably
think
still
about
don't
it.
get
Is
it.
it cheating if you write like a formula on your head?
Yes.
Yeah, I did that, but,
You got caught.
yeah, I wrote it on my brace for bio in ninth grade.
Wait, what formula did
And
you
you're
write?
still here?
Yeah.
What formula did you
Or
write?
like, I wasn't sent to Mr. Brown since I was in like ninth grade.
Oh, nice. Now.
Oh, so the teacher just,
Yeah.
Do you have
the
a
teacher
wall?
just took care
When I was
of it.
Wareheim.
Wait, what
Why not?
equation did you write on it though?
No, it was for bio.
Well, I'm glad we got all this on video.
What did you write on it?
Like the stuff.
Probably like
Key
the.
phase, meta phase stuff.
Oh,
That's
those
all
are
you-
hard.
I don't know.
Those are hard. That's hard.
Just be mad.
Okay, how do you solve for z in this equation? Z squared is equal to 4 minus x squared plus. See, anytime you have x squared plus y squared, that's like a hint you're gonna do it polar coordinates.
Oh,
Right? Because x squared plus y squared is r squared.
Where'd you get the 4?
It's given in the problem.
Oh.
There. We're trying to solve for z. Z equals the square root, because it's gonna be the upper half, right? 4 minus x squared plus y squared. Okay, so what do I plug in for z right here? What am I gonna put? What am I plugging in for z?
Square root of
Yes.
4 minus r.
4 minus r squared. And then, like we said, what is r gonna go from? 0 to 1. And theta goes from 0 to 2 pi. And look at that integral, right there. How do I integrate that? Wong.
You use
Oh.
u substitution.
Yes, u substitution. U equals 4 minus r squared, right?
Yep.
Okay, that one you can do. I thought we were gonna be done already, so I could get ice.
Hey!
You get ice?
I mean, ice for the math team practice.
Don't-
Our drinks need to be cold, otherwise we can't focus.
Hey, it's so great. Oh, yeah.
You guys,
I didn't do
This is-
How
this
come
is the
one of
last
your-
year of doing this
How come one of
class.
your team members had to bring like juice and?
The only reason I would stay and teach it one more year is because of
Jonah Yoshi.
Yoshida.
Oh, how cute.
After that, everybody else.
What about the 18?
We need a new teacher.
That is
No,
Jonah.
we need a younger teacher that can tolerate your
Alan, yeah.
infantile shenanigans.
You tolerated Trevor and James.
Huh?
You tolerated Trevor and James.
Oh, we can't be that.
No, they did an independent study.
We're like they
Oh,
All
why
they
didn't
did is come in and take the test. They didn't even ask for help. That's what independent study means. You're doing it by
We
yourself.
don't have the.
Ganas, you don't have the ganas.
Excuse me.
Okay, now today, finally, we get to triple integrals.
Oh my god.
So we use triple integrals to compute volumes. Okay, let's do an example of how to set up a triple integral. Okay, can anybody think of a volume you want to come? Shall we do that paraboloid thing again?
Can you just do a sphere?
Okay, that's even harder, but.
Really?
Alright.
Yeah, okay, you want to compute the, we're not going to actually compute it, I'm just going to set it up for you.
Oh. It's just same, but you.
Let's
you-
do
Okay, let's do the parabola. Let's just do the paraboloid. So z is equal to yeah, x squared, no, 4 minus x squared plus y squared. Now, like I showed you last time, if you do see this, you want to use polar coordinates, but tonight's homework is all rectangular coordinates. So if you see something like this, you're in for a mess. But look at the problems. I think two of the, look, the first two problems, you just have to write an integral. You don't even have to compute it. It just says write an integral, set it up. In fact, on the test, I think there's 2 or 3 problems where you just have to write the integral.
So you get it wrong.
I'll give you a hint. One of them, you do it using rectangular, the other one using cylindrical, and the last one using spherical. Don't worry, we're gonna get there, but we're not there yet. So, in 3 dimensions, rectangular coordinates, if you take a tiny, infinitesimally small cube like that, you know what? Why am I drawing it small? Just imagine this to be infinitesimally small. What would the dimensions of it be? dx, dy, and dz, right? So what would the volume of the very tiny piece be? dx times dy times dz. And then what you're going to do is just add them up. But like I told you the last time, the hard part is figuring out what the limits of integration are going to be. So in this particular problem, let's write this up. dx, dy, dz, okay? And we're going to go triple integral. Now, the first integral, you know what? I think we should do it with respect to z first. Okay, so this is a paraboloid. Let me attempt to draw this again. Where's Lum? We need Lum to draw this. Like that? That's pretty ugly, yeah? So z is going to go from here to from the bottom z to the upper z. So what's the bottom z since it's the xy plane?
Or 0.
0. And what's the upper z, which is the paraboloid?
4.
4 minus x squared plus y squared. So that's the limits for the z. Okay, now we go for the limits for y. So how do you figure out the limits for x and y? So what you gotta do is you gotta take this and smash it down onto the xy plane. Like if you have this paraboloid and you just smashed it down onto the xy plane, what would you see?
A circle.
Yeah, it would be a circle of radius 2, yeah?
Yeah.
Smash it down onto the xy plane. That's omega. Okay? So y is going to go from this to that. So what's the equation of this? Y equals
4
root 4 minus x squared negative. And then this one is y equal positive root 4 minus x squared, right? So your limits of integration for y are going to be the y on the bottom to the y on the top. Negative root 4 minus x squared to root 4 minus x squared. And then the last one always has to be constant. So x is going to go from here to here. So what would that be? Negative 2 to 2. So you the last one always has to be the one with the constant. Oh, sorry, and I forgot to write the dx because we're doing that last. There you go. This integral, when computed, will give you the volume of the paraboloid bounded by the xy plane. So I would think in most cases this is what you're going to do, because normally curves are given as z equals something. So you're going to go from the z on the bottom to the z on the top. And then when you integrate with respect to y, smash it down onto the xy plane, then you go from the y on the bottom to the y on the top, right? And then the last one, you go from where the x value here to the x value there, whatever the graph looks like. Yeah.
What if the shape, like when you smash it down, isn't like a perfect circle like that?
Well, it has to be something where you can figure it out, though. Yeah, it's not always going to be a circle.
Well, can you, what
Like it
what
could
other
be,
shape
could
might
be
square.
like an ellipse, could be a square.
Yeah.
Well, like in number 4, it's just a triangle.
Can you start us off on that?
No, you guys need to at least try this, man. Okay, so there, that lesson was pretty easy. Now, in real life, you wouldn't compute this using rectangular coordinates because it's going to get messy. So, like I told you before, whenever you see this, probably you're going to do polar, which is cylindrical coordinates. Yeah? You want to do a quick review of cylindrical and spherical coordinates because it's coming up?
With cylindrical, you would just do the
Okay,
same
so-
thing that we did with polar, but then with an extra dz, right?
Yes, exactly. So XYZ, that's rectangular coordinate system. R theta Z is, we call that cylindrical coordinates. So basically, it's like this. R and theta are the same r and theta in the polar coordinate system like that, just like this is x and y, except you got the z coordinate coming up like this, yeah? R, theta, z, so that's nothing new, that's the same polar coordinates we learned in 11th grade or last year, yeah? But, so spherical coordinates, rho, theta, phi. That one kind of hard to draw, gotta do it in 3 dimensions. So if this is the x, y, and the z axis, let's draw the box again. Remember the box? So if this is the point, rho, this is not p now, this is the Greek letter rho, is how far you are from the origin. So if this is the point, that distance is rho. Theta is the same theta as in the polar coordinate system, see? So on the xy plane, you know how when you draw the triangle, this is x and this is y and this is z? In the xy plane there, that's theta. Just like that, if you're looking at it at an angle like that. And then phi, you guys remember what phi is? Phi is the angle that this segment or vector, whatever, makes with the positive z-axis. That's what phi is. That's called the spherical coordinate system.
Wait, what is the first one called, the XYZ?
Rectangular. Rectangular, cylindrical, spherical. So, here, general rule of thumb. If you see x squared plus y squared prominently in your integral, you're probably going to integrate in this coordinate system. If you see x squared plus y squared plus z squared prominently in your integral, then you're going to want to use this one. You know why? Because x squared plus y squared plus, look at that picture. What is x squared plus y squared plus z squared equal to?
1.
No.
Oh, what's that?
Z.
Rho squared.
Oh.
Rho squared. So then, if you make that substitution, the integral becomes a lot easier. So that's why we have these different coordinate systems to make integrals easy. Now, of course, if you're doing this in real life, if you're an engineer on the job, you know what you're going to do, right? Wolfram alpha.
Yeah.
But still, the engineer got to set up the integral, right?
Oh.
That's the hard part. So you got to be able to set up the integral so Wolfram alpha can compute it.
Well,
Technology
I'm
will
not
get
an
advanced
engineer,
enough.
so-
by
You
that
know what I
point.
don't understand? How does like integrals and stuff apply to like,
Real life.
yeah, real life?
Oh, you took calculus last year. You compute areas and volumes.
Come on.
Or like the something underground. the-
Okay, here.
That thing.
We're related races.
Hey, can you like show us like, a
Okay,
real
like-
life example?
Okay,
Air
you
balloon.
guys know how to figure out areas of regular figures like that, right? But in real life, figures aren't like that. So like
Yeah.
you know, like in physics, you had time versus velocity. This is the kind of problems you had, right? What was the displacement or the total distance traveled by the particle? Don't you just compute these areas right there?
Yeah.
This is how much the particle traveled to the right, that's how much it traveled to the left, right?
Yeah.
But in real life, is that what the velocity looks like? No, lots of times the velocity gonna be like things that look like just.
Oh, okay.
So we have to be able to compute these areas somehow, because it's not always gonna be like nice shapes like this. That's where calculus comes in.
Do you know the equation of that?
Yeah, so if you know the equation, no, because even if you don't, what did we learn last year? You can break it up into rectangles, and you can use LRAM, left Riemann sum, right Riemann sum, midpoint Riemann sum, trapezoids. Remember all those things we did? And then you can have a computer add up 1,000,000 of them really quickly, and then that will be a very good estimate of it, yeah? So that's why calculus is just a tool to help us like study physics. That's what Sir Isaac Newton did. That's why he invented calculus, because he knew he had to figure out the area, but how do I figure out that area? And then he came up with integrals, Riemann sums.
The apple fell on his head.
He's just like, oh, integral. How did you come up with this?
Okay, oh man, only got